drew a lot of structures here. One of the tasks you may be assigned in organic chemistry is to find all the constitutional isomers for a given molecular formula, like C₇H₁₆. How do we do that? The biggest piece of advice I can give you for finding all constitutional isomers is to work systematically, not haphazardly. If you randomly try and draw a bunch of different structures and hope you find them all, you might not, and you might get pretty frustrated. Work very systematically when you do this exercise. The way to do that is to start with the formula and the number of carbons and ask yourself how many ways are there to arrange 7 carbons. To start with, one way to arrange 7 carbons is all 7 carbons in a row, and that's the first step. First, draw the longest non-branching hydrocarbon you can given the number of carbons, in this case 7. I'm going to use this shorthand of 7C plus 0. What I mean by that is we're going to start with a 7-carbon chain that has no other carbons branching off of it. We're starting here because that's how many carbons we're allowed to start with. The first structure we draw then is all 7 carbons in a row. This is our first constitutional isomer, and it is the 7-carbon hydrocarbon heptane. Going back to our question, how many ways are there to arrange 7 carbons? We just found a way to arrange 7 carbons with nothing branching off. The next thing to do is to go 1 carbon shorter, make a 6-carbon hydrocarbon as a template. That won't be a unique structure, but we'll use that 6-carbon template to add on 1 more methyl group to make new constitutional isomers. We start with the 6-carbon hydrocarbon. This would be hexane. This is not a constitutional isomer because it does not have 7 carbons. But we can add a methyl group systematically to each position down the line to see if it forms a new structure. Sometimes it will, sometimes it won't. For example, we could put the methyl group on the first carbon branching down like this. Is this a unique structure? Ultimately, no. Ultimately, this is still just a 7-carbon straight chain hydrocarbon with 1 carbon rotated down. So this is ultimately equivalent to heptane. But what we can do is move this methyl group systematically down the line, and that will form new isomers. We could put the methyl group at carbon number 2, or carbon number 3, or carbon number 4, or carbon number 5, or carbon number 6. Let's see how many of these are new isomers. This structure would be 2-methylhexane, and this would be a new isomer. This structure would also be unique. This structure would be 3-methylhexane. This next structure would be 4-methylhexane. However, that's actually not a unique structure. This is just a steering wheel rotation of 3-methylhexane. If you're not familiar with steering wheel rotations, watch my video on manipulations of molecules that I've linked to down below. So while we can move this to what looks like a new position, this structure is ultimately the same as this one and not a unique structure. Same thing with what looks like 5-methylhexane. 5-methylhexane is really just the same as 2-methylhexane, and so this is also not a new unique constitutional isomer. And finally, 6-methylhexane is the same as regular heptane, and so this is also not a unique structure. Most of the time when we draw structures, they'll ultimately end up being equivalent to another structure we've already drawn. That's why I include the caveat, you really don't have to go past halfway. Once you get to the halfway point, everything after the halfway point will likely be identical to something you've already drawn. The next set is the C5 plus 2 set, where I start with a 5-carbon template and systematically add on 2 more carbons. Turns out there are 2 ways I can do this. I can keep those 2 carbons together as an ethyl group and move the ethyl group systematically down the chain. Or I can take 2 individual methyl groups and put those 2 methyl groups in all possible positions down the chain. Hopefully you can see if I add the ethyl group to the first position, this is ultimately the same 7-carbon straight chain hydrocarbon, just rotated. This is the same as heptane and not a new unique isomer. What if I move the ethyl group to the second position? Is this a new unique isomer? It sure looks like it, but let's see what its name would be and see if it's actually unique. The longest carbon chain would be these 6 carbons, and this methyl group would be coming off of the 3rd carbon. So this is ultimately a rotation of 3-methylhexane. This is ultimately the same structure as 3-methylhexane, just rotated. You have to be very careful when you're doing the systematic analysis that the structure you've drawn is really unique and not a rotated version of something else. You can check your work by giving your structure its IUPAC name, and that IUPAC name needs to be unique and not identical to any structure you've previously drawn. I can draw the ethyl group off of the 3rd position. Is this unique, or is this the same as anything else? If I were to give this molecule a unique name, 5 carbons would be the parent hydrocarbon, and this would be 3-ethylpentane. That's an IUPAC name I've not used before, so this structure, yes, would be a new unique isomer. If I move the ethyl group continuously down the chain, I'm going to find that these are identical to ones I've drawn previously. I passed the halfway point here, so I don't technically need to draw these, but if you need to, it's good to prove to yourself that this is also identical to 3-methylpentane, and when we have it on the end, this is the same 7-carbon hydrocarbon, this is identical to heptane. But an ethyl group is not the only way to satisfy the C5 plus 2 set. We can also have 2 individual methyl groups that we add to the molecule. And we should do that very systematically as well. We'll start by putting both methyl groups on carbon 1. We'll keep 1 group on carbon 1 and move the other methyl group systematically down the chain. Then we'll put both methyl groups on carbon 2, keep 1 group on carbon 2, and move the other methyl group down the chain. Then carbon 3, and so on until we've exhausted all possibilities. Yes, this is going to be a little bit tedious. We're going to end up drawing 11 structures, but not all of them will be unique. And as you work through this process, you'll start to see I can stop at the halfway point, and I'm not going to draw any more unique structures. So if I draw the methyl group on carbon 1 and the other methyl group coming off of carbon 1, is this a new unique structure? Give it an IUPAC name. The longest chain would be 6 carbons here with a methyl group on carbon 2, so this ultimately would not be a new structure. This ultimately would be the same as 2-methylhexane that we've drawn previously. And in fact, by keeping this methyl group on carbon 1, as I move the orange methyl group down the chain, they're all going to be derivatives of hexane. I've gone back to my C6+1 set, so I can stop this set now because there's no way I'm going to be able to keep a methyl group on carbon 1 and draw a unique structure. Next, I can put both methyl groups on carbon number 2, leave one of them on carbon 2, and walk the other one down the chain. If I put both methyl groups on carbon 2, this now is, yes, a new unique constitutional isomer. We'd have 2 methyl groups on carbon 2 of a 5-carbon chain, so this would be 2,2-dimethyl-pentane as a new unique isomer. I'll now walk the orange group down the chain. I'll leave the blue methyl group on carbon number 2 and put the orange methyl group on carbon number 3. Is this a new unique isomer? This would have a 5-carbon parent with a methyl group on 2 and 3. Yes, this would be a new unique isomer. This would be 2,3-dimethylpentane. Next would be to leave the methyl group on carbon 2 and move the next methyl group over to carbon number 4. This also would be a new unique isomer, 2,4-dimethylpentane. Leaving the blue group on methyl 2 and moving the orange methyl group over to carbon 5 ultimately makes a non-unique structure. This is going to end up being a 6-carbon chain with a methyl group at carbon 2. So this also will be identical to 2-methylhexane. This is not a unique constitutional isomer. Systematically, the next choice would be to put both methyl groups on carbon number 3. And this, yes, will make a new constitutional isomer. With both methyls at carbon 3, this would be 3,3-dimethylpentane. Keeping the methyl group on carbon 3, the last 2 options will be to move the methyl group to carbon 4 and carbon 5. If I move the methyl group to carbon 4, this is going to be a pancake flip of 2,3-dimethylpentane and not a unique isomer. And if I move it to carbon number 5, this is going to be equivalent to 3-methylhexane, which is not going to be a new isomer either. After this structure, all of the new methyl groups will go past the halfway point, so we would not expect any of these to be unique. If I put both methyl groups on carbon number 4, this is going to end up being equivalent to 2,2-dimethylpentane. If I put one on carbon 4 and one on carbon 5, this is also going to be equivalent to 3-methylhexane. And if I put both carbons on carbon number 5, this will be equivalent to 2-methylhexane. This is the end of the C5+2 set. We drew a lot of structures here, but we actually found quite a few new unique structures. We found 4 new unique constitutional isomers in this set. The next set would be the 4 carbons plus 3 set, starting with the 4-carbon template, systematically adding 3 additional carbons. You might be asking yourself, how far do we need to take this? You could certainly go all the way down to the C1 set, but you don't really have to. Similar to the principle we saw before, we can stop when we get to the halfway point. Once we start chopping off more than half of the carbons and trying to add them back on as substituents, all of those will end up being identical. So in this example, with 7 carbons, after I chop off 3 carbons, I can stop. 4 carbons will be more than half of the carbons. So the 4 carbon plus 3 will be our final set. Chopping off 3 carbons and adding them onto the molecule will be our final set. With this one, there are 4 different ways we can add those 3 carbons back. We can add them on as a straight chain propyl group, as an isopropyl group, as an ethyl and a methyl group, or as 3 methyl groups. Let's take a look at all of those. If I add the propyl group onto the end of the molecule, as we've seen time and time again, this will just form the straight chain isomer and not be a unique isomer. This will be identical to our original heptane molecule. If I add that propyl group to carbon number 2, this will also not be a unique molecule. This will be a molecule that has 6 carbons in its parent carbon with a methyl group coming off of carbon 3. This will be the same as 3-methylhexane. That makes it to the halfway point, so I don't need to add the propyl group on the other half of the molecule. Those will be identical to the 2 I've already drawn. The next way to attach 3 carbons would be an isopropyl group. Pause the video, see if you can figure out all the ways to add an isopropyl group to a 4-carbon template. I can start by adding that isopropyl group to the first carbon. Is this unique? This will form a parent with the longest chain of 6 with a methyl group on carbon number 2, so no, this is not unique. This will be identical to 2-methylhex. I can also add that isopropyl group to carbon number 2. Is this going to be unique? The longest chain here is going to be a 5-carbon chain with a methyl group at carbon 2 and carbon 3. So no, this will also not be unique. This will be the same as 2,3-dimethylpentane. Finding the IUPAC name is going to be really key to determining if these molecules are identical, even when they don't really look the same. That also brings us to the halfway point of the molecule. We don't need to add the isopropyl group to the other 2 positions. They'll be the same as each other, which are already the same as previous molecules we've drawn. Those are the 2 ways to add the 3 carbons, keeping all 3 carbons together, but we can also separate them out into an ethyl group and a methyl group. I can start with the ethyl group on position 1 and add the methyl group down each line, and move the ethyl group over to carbon 2 and add the methyl group, and so on. Hopefully you can see that we don't need to add really either group to carbon number 1. Doing so would just extend the longest carbon chain, making it identical to one of the other sets that we've previously drawn. Anything with the ethyl group on carbon 1 would be identical to the C6 set that we've previously drawn. The next molecule I can draw has the ethyl group on carbon number 2 and the methyl group on carbon number 2 as well. Is this unique? The longest carbon chain would be 5 carbons long with methyl groups at carbon 3, so no. This will be identical to 3,3-dimethylpentane, a molecule we've already drawn. Next would be to keep the ethyl group at carbon number 2 and to move the methyl group to carbon number 3. Is this unique? Let's find the longest chain. 1, 2, 3, 4, 5, a 5-carbon chain with methyl groups at carbons 2 and 3. So again, this is going to be identical to 2,3-dimethylpentane, a molecule we've already drawn. If I leave the ethyl group at carbon number 2 and move the methyl group over to carbon number 4, this has a longest carbon chain of 6 with the methyl group at carbon number 3. So this is going to be equivalent to 3-methylhexane, a molecule we've already drawn. The next molecule I would draw would have both the ethyl and the methyl group on carbon 3 past the halfway point, and with all the substituents constituents past the halfway point, those will always be identical to something we've already drawn. So it looks like there's no new unique ones with an ethyl and a methyl group. The final way to add all 3 carbons is to have 3 individual methyl groups. Let's take a look at that. What I want you to see is you don't really need to add any of the methyl groups to carbon number 1. If you add any of the methyl groups to carbon number 1, that's automatically going to increase the carbon chain to 5, and that's going to make them all identical to the C5 isomers that we've already found. This one would be identical to 2,2-dimethylpentane, a molecule we found previously. The next thing to do would put all 3 methyl groups at carbon number 2. Can't do that, that would be 5 bonds to carbon, but I can start with one of the methyl groups on carbon 2, and the second methyl group on carbon 2, and the next choice would be to put the next methyl group on carbon number 3. Let's take a look at that. The longest carbon chain in this one looks like the longest carbon chain is going to be 4 in all cases, so that's going to be a butane with methyl groups at 2, 2, and 3. We have found a new isomer. It took us a long time, but we did finally find one more isomer. This will be 2,2,3-trimethylbutane. The next structure would keep both of those 2 methyl groups at carbon number 2 and move the final methyl group down to carbon number 4. That's going to end up being the same as 2,2-dimethylpentane we previously found. Next, I can try keeping one methyl group at carbon number 2 and moving the other methyl groups to carbon number 3. This is ultimately going to be a steering wheel rotation of the 9th isomer that we just found. I can keep the blue methyl group at carbon number 2, the orange methyl group at carbon number 3, and move the red methyl group over to carbon number 4. This is not going to be a unique isomer. This is going to have a longest carbon chain of 5 carbons with the methyl group at carbons 2 and carbon 3. So this will be the same as isomer number 6, 2,3-dimethylpentane. Then I can keep the blue methyl group at carbon number 2 and move both the orange and the red methyl groups to carbon number 4. This is also not a unique isomer. This is going to have a longest chain of 5 with methyl groups at 2 and 4. This is going to be identical to number 7, 2,4-dimethylpentane that we previously found. And that's really going to be all the isomers we need to draw. The next choice would have 2 methyls on carbon 3 and 1 on carbon 4, but that puts all the substituents past the halfway point. So by necessity, these are always going to be identical to ones that we've already found. This one would be identical to 3,3-dimethylpentane that we found earlier as isomer number 8. And that's going to be all of the 4 carbon plus 3 isomers that we need to draw. And that's also going to be the end of this exercise. The next thing would be 3 carbons plus 4. I would remove 4 carbons from the original molecule. But removing 4 carbons would be removing more than half of the original carbons, and so all of those by necessity will be identical to ones we've previously drawn. Once we reach that halfway point, we can stop. There we have it. These are the 9 structural isomers of C₇H₁₆. We did that through a very systematic process, so you can take any molecular formula you're given, systematically try and find all the combinations of ways to arrange that number of carbons to find all the possible constitutional isomers.
Thanks for watching. If you like what you saw today, maybe let your instructor know about these videos, or your friends at other schools. Check out some of these other videos and playlists, see what you like. As always, don't forget to like and subscribe.